Yeah. Just check. Is the audio working properly there? Sure. Okay, great. Uh, yeah, try to come slightly ahead because I won't be able to screen. So, as far as possible, just come ahead. Hmm? Battery is not working. Yeah, if possible, just come ahead. Hello, if possible, just come ahead. Otherwise, you won't be able to hear me. I mean, you can occupy this space. Hmm? What? I have no idea. It was there when I came, I suppose. Just let it stay here. If no one else takes, then you can take it. Okay. So should I start? Fine. Thank you. Okay. Yeah. So today I am going to talk about. Can you hear me? Last row. Okay. That's the acid test. Okay. So today I'm going to talk about certain subring of QX. So the talk is going to be elementary, at least I hope so. So anyone who is familiar with rings, ideals, what are prime ideals, what are maximal ideals, what is irreducibility, what is a prime, uh, and UFDs, PIDs, of course, then he or she will be able to follow it, at least hopefully. So whenever, if there is any problem, if you are not able to follow me, please stop me and ask. Okay. I mean, don't assume that something hi-fi is going on. Okay. So, in particular, I'm interested in this ring, which is defined as, sorry, where is it? This is, see, x is defined to be a naught plus a1x plus up to plus a x to the power n belongs to qx such that, so if I am only interested in the polynomial ring over rational numbers, then all the coefficients are naturally coming from the field of rational numbers. So therefore, this is a subring, actually a proper subring. So I'm going to put one condition. The condition would be, okay, the constant term of the polynomial is coming from the ring of integers. Okay. Now, as you can see, instead of integers, you can take other subrings of Q, and that will lead to various different subrings. Okay, and all of them are kind of interesting. And perhaps, I mean, most of them you can, maybe all of them you can actually construct using this R. Starting from R, you can do something, and you will end up with some other rings. Okay. Now the point is that this ring R, it is sitting between two very nice rings, right? Now what about this? So first of all, QX, I hope all of you know it's a PID. Okay. So every ideal is principal as well as there is an integral domain. On the other hand, ZX unfortunately is not a PID, but at least you are starting with a PID. So because of Gauss's result, you will end up with something which is a UFD. And it is not too far from a PID in the sense that if you know dimension theory, then you would be able to see that this is a two-dimensional ring. Okay, so it is not too far from a PID, and every ideal in this ring can be generated by two elements, not one element, but two elements. For example, you can take this ideal, and every maximal ideal kind of looks like this. Like this means it can be proved that if I pick up any maximal ideal from ZX, it will always contain a prime number inside it, and once you go modulo that prime number, it will become something like z mod pz then adjoint x. Okay, and that's a polynomial ring over a field. Therefore, every it's becoming a PID. Therefore, every ideal can be generated by single element. If you leave that generator, that will give you the maximal ideal. Okay. So this is a very nice ring. This is a very nice ring, and R is sitting inside it. I mean, sitting in between the two. So it is natural to expect that maybe R is a very nice ring too. However, in the course of this talk, we are going to see that's not the case. R is not a UFD. It is not even a noetherian. If you are familiar with the terminology, it simply means that there are ideals of R which are not even finitely generated. Okay. Now here every ideal is generated by at most two elements. Here every ideal is generated by exactly one element. However, in between something is sitting where not every ideal is even finitely generated. Okay, so let me just list. I mean, in the discussion, we are just going to list down some properties of this ring R. So to begin with, the easiest one to find out is what are the units. Can you tell me what are the units of R? So this is the notation which I am going to use to denote the set of units of R. So can you tell me what are the units of this ring? Yeah, plus minus 1, exactly. So why so? Because if I, first of all, whatever unit you pick here, it will remain a unit in Qx. Now inside Qx, the units are only non-zero rational numbers. However, in R, the first coefficient is coming from the ring of integers. Therefore, the only possible units in R are plus minus 1. Okay. Number 2, note one more thing. These three rings are kind of closely related in the sense that if I pick up any ideal I from R, so again this is the notation I am going to use to denote ideals, then I intersection Zx is that obvious? So whatever ideal I pick up, so of course before that I should be a non-zero ideal. So if this is not equal to 0, then if I take its intersection with Zx, that's again non-zero. That is again kind of obvious because whatever I pick up, it contains a non-zero polynomial. Now non-zero polynomial, what can happen? In the non-constant terms, there may be things in the denominator. So what you do? To clear out the denominator, you get something which is in Zx. Okay. Similarly, if J is a non-zero ideal coming from Qx, then I have for the same reason essentially. So again, what you have to do, suppose it does not have any constant term, then you don't have to do anything. The condition is there already. Otherwise, if it has some constant term, which is a rational number, which is not an integer, again you clear the denominator, puts it inside R. Okay, number 3. Now, surely the surprises begin. So if I pick up any prime number, then P divides x to the power n for all 1. Is that clear? Actually, you do not need P to be a prime number. If it happens to be any non-zero integer, it divides x to the power n for every n greater than equals to 1. Why? Because in any coefficient which is greater than the constant term, you are allowed to divide inside R. Okay. Fine. So what follows? What follows is the following. R mod PR is isomorphic to Z mod, which is usually denoted by FP the finite field consisting of p elements. So why is it true? See, if I pick up any prime number, then p divides all x to the power n for all n greater than or equals to 1. Therefore, the ideal generated by p contains the entire thing starting from x. It contains x square, and so on. Okay? So therefore, when I go modulo p, starting from x, everything goes to 0. So what remains? Essentially, what remains is z. Then you have to go modulo p. Okay? Therefore, R mod PR is nothing but z mod pc, which is nothing but fp. Is this clear so far? Okay. So this implies PR is a maximal ideal of R. Okay. Fine. Any question? No. Now, at the beginning, I said that this ring R is neither a UFD nor it's Noetherian. So why? That's very simple to see. To look at this chain of ideals and so on. Okay. Now, why is it a proper chain? It's a proper chain because half is the number by which I am multiplying every generator of one ideal to get the next ideal. That is something which is not contained in R. Okay. How do you get x by 2 using x by 4? You have to multiply it by half. However, half is not present in R. Therefore, we get an strictly increasing chain of principal ideals. Now it gives us two things simultaneously. First of all, it shows that the ring is not Noetherian. Because one equivalent criterion for Noetherian rings is that you cannot get an infinite increasing sequence of ideals. Okay? Here we are getting principal ideals. But because this is an infinite chain of principal ideas strictly increasing, it also immediately tells us this is not a UFD. Why this is not a UFD? Because if it is a UFD, you can never get a strictly increasing chain or sequence of principal ideals, because what happens? Suppose it's a UFD. Then if you are starting with some element, it must have a prime factorization. Look at the next generator. That divides the first generator. Now, if these are say R many prime factors, then in the next generator, because it divides the first generator, it cannot have more than R minus 1 prime factors, because you have to drop off at least one. If all the prime factors are also present there, then they will become associates. Okay? Because we are getting a strictly increasing chain, in the next stage you will have at most R minus 1 prime factors. In the next one you will have at most R minus 2. And because we have only finitely many prime factors, eventually we will exhaust everything. Okay? So therefore, this increasing sequence of principal ideas immediately tells us two things. It's neither Noetherian nor it's a UFD. Is it clear so far? Okay. And just one remark, X is not irreducible. I suppose that's obvious. Because what I can do, I can take just 2 into x by 2. None of them are units. Okay? Okay. Now, if J in Qx is the principal ideal generated by X, then J intersection R is not, I said it's not even finitely generated. Why? See, if you look at Qx, you have some ideal here generated by X. I'm intentionally avoiding writing it inside round bracket X because that will, I'm going to consider it as an ideal in three different rings. One is Qx, another is R, another is Zx. Okay, so it is better not to denote it by round bracket X. And then I have Zx. So if I start with the ideal which is X, maybe let us write it like this. Once you come down to R, you get something which is not finitely generated. What is that ideal? That ideal is simply J intersection R is generated by Rx such that you can see this is not finitely generated. In fact, whether this ideal is finitely generated or not is equivalent to the question whether Q is a finitely generated abelian group. Is that clear? Why? Because, see, first of all, is it clear that J intersection R is nothing but the ideal generated by elements like this? Because all, yeah, no, R belongs to Q. This is a generating set. See, first of all, if you take X, you take the intersection. Intersection definitely contains X. But now think about X by 2. It is also there because upstairs in Qx I am allowed to divide by half. So whatever rational number I take, Rx is there upstairs inside the ideal generated by X, so, and it is below. Therefore, everything in the form Rx are there in the intersection, and the intersection ideal will be generated by elements like this. Because everything higher you are allowed to divide by rational, you are allowed to divide by whatever integer you want. The only problem is that the constant term is an integer. Okay. Now you can see that suppose I take only finitely many of them. Say R1x, R2x, say Rnx. Then the point is that these finitely many elements cannot generate this ideal, because suppose if I write some r prime x equals to sum of fi and rix, I equals to 1 to n. Now what happens? You have to concentrate on the coefficient of x. Therefore, what is there in fi's, it does not matter except the constant terms of fi's. But in R, every polynomial has constant term and integers. Therefore, if r prime x equals to sum of fi rix, we better have r prime equals to sum of fi naught, the constant term, and ri. Is that clear? Therefore, whether you can get hold of every rational number using R1 up to Rn, it becomes that question. And I suppose all of you know, if you don't, please take it as an exercise, that the Q plus is not a finitely generated abelian group. Okay? The finite generation of Q as a group is equivalent to saying whether this ideal is finitely generated or not. And we know that is not the case. Okay? So, J is a prime ideal inside Qx whose intersection with R is a prime ideal which is not finitely generated. Clear? And this is one exceptional ideal. We will see why I am calling it exceptional, which I am going to denote by P naught. Okay? Okay. Okay. Our next job is to trying to figure out what are the prime elements and what are the irreducible elements of R. So what have we seen so far? Every prime number remains a prime element in R. In fact, they generate maximal ideals. Going modulo them, you get finite field consisting of p elements. Okay. So what happens for polynomials which are not constants? So we completely know that if you have a constant polynomial inside R, it is going to give me a, well, before that, if I take any particular integer, okay, then R has a prime factorization inside Z, and every prime number they remain primes in R. Therefore, that is going to give me a prime factorization of R in capital R also. Okay. Therefore, any integer which is not a prime is not a prime in capital R. And if it is a prime, then it becomes a maximal ideal in capital R, where the quotient is nothing but fp. Okay. So the constant polynomials are done. We can completely see which gives me prime elements, which does not give me prime elements. So let us look at polynomials which are not constant. Then what happens? So suppose f belongs to R is not constant. So by this I simply mean that it's a polynomial of positive degree. Okay. Then if is irreducible implies f0 equals to plus minus 1. So f0 is simply the constant term of it. Now why so? Suppose f is a polynomial whose constant term is not equal to plus minus 1. Okay. Then what I can do, suppose its constant term is some a minus just a moment. What did I say? Yeah. So first of all, then yeah. So first of all, what can happen? If f0 now is not equal to plus minus 1, can it be 0? No, because we already observed that x is not irreducible. 2 into x by 2. Therefore, it better be a non-zero integer. Okay. So suppose that non-zero integer is a. Then I can write a into f by a. Okay. So what happens? F equals to a plus a1x plus say a nx to the power n. Now the point is that I can divide all the coefficients starting from the degree 1 by whatever integer I like, because they are allowed to come from the field of rational numbers. Only problem is this one. So if I extract a out, it will be simply 1 plus but now this fellow is a perfectly nice member of capital R. Okay, the only restriction was about the constant term. And because a is not a unit, small a. So when is that a unit? That's a unit in capital R if and only if you all agreed it's plus minus 1. So unless a is plus minus 1, that's a non-unit. Now this fellow is a non-unit because everything is happening inside Qx. And inside Qx, we are not allowed to invert polynomials of positive degree. Therefore, whenever the constant term of f is not a unit, we can write it as a product of two non-units. Therefore, it is reducible. Am I clear? Therefore, if you want f to be reducible, the constant term must be plus minus 1. However, the converse is not true. That means it can be plus minus 1 and still be reducible. That is easy to see. Into this. Okay. It can very much, I mean, it can very well happen that you have the constant term 1 and still it is reducible. Okay, so what is the condition? Okay, so now just keep the entire story in mind that we want to find out what are the irreducible elements of capital R. So we just observe that if you look at constant polynomials, then only the ones which are coming from prime numbers, they are irreducible. Anything which is not prime is not irreducible. Next, we are going to polynomials which are not constants. That means they have degree greater than equals to 1. In that case, if it is irreducible, then its constant term must be plus minus 1. Now we are trying to see whether that, well, we just saw that that is not a sufficient condition. Certainly it is necessary. Okay. So what is the sufficient condition? The sufficient condition is that suppose f belongs to R is a non-constant polynomial. Together with the condition f0 equals to plus minus 1. Okay, because it is a necessary condition for a non-constant polynomial to be irreducible. Okay, suppose f0 is not plus minus 1, then f is irreducible in R if and only f is irreducible in Qx. Just think about it for a moment. It's very easy. Now, is it clear that it is irreducible in R if and only if it is irreducible in Q? See why? This condition is, I think, essential. So, suppose if is irreducible in R, or maybe it is easier to see the other way that something is reducible, then it is reducible. So, suppose it is reducible in R, what does it mean? It means that you can write it in the form GH, where G and H they are coming from R. Okay. Now, if both G and H they are polynomials of positive degree, I am already done because that gives me a decomposition over Qx also. So, the what is the possible problem? The problem is that maybe some of those G and H are units, which will become units in Q, but that is not possible because the constant term is plus minus 1. Okay. So, the constant term of both G and H will be either plus 1 or minus 1. Therefore, if this gives a non-trivial decomposition of A over R, then it gives a non-trivial decomposition over Qx. Fine. Now what about the converse? Suppose F is equal to G into H and G and H are uh, non-constants in Qx. So therefore they are polynomials of positive degree. Now what is the problem? The problem is that maybe the constant terms of G and H they are not integers. Okay. But then what do? You just multiply them by their inverse to bring it inside R. Is that clear? So then I take G by G naught, which will make the constant term 1, and H by H naught. Of course, maybe let's assume that, see, if whether F is irreducible or not, it does not matter whether I multiply F by a unit. So therefore, I can freely multiply F by plus 1 or minus 1. So therefore, we can actually assume that the constant term is 1. There is no harm in assuming that. Okay. Now, what is happening here? Here in this product, G naught into H naught, that is equal to 1. So I can divide the product GH by as well as by G naught into H naught. Now when you take G by G naught, the constant term has become 1. When you take h by h naught, the constant term has become 1. Now I have a factorization of f in terms of two polynomials of positive degree. Now the polynomials are coming from R, okay, which are not units. Fine. So therefore, is it clear that if f is a non-constant polynomial with a constant term plus minus 1, then if it happens to be irreducible in R, that is possible if and only if it is irreducible in Qx. So to check irreducibility of non-constant polynomials in R, we can actually check its irreducibility in Qx. No problem. But one thing you have to ensure the constant term is plus minus 1, but then again, it does not matter. If you are looking at Qx, you can divide it by the constant term. So irreducibility of a polynomial in Qx does not matter. You can multiply it by whatever unit you want. Therefore, you can always assume that the constant term is 1. Just like you always assume that the irreducible polynomial is monic. It's just like making it monic. Okay. Now this is very nice criterion because over Qx we know what are the irreducible polynomials. Actually do not know, but is theoretically it is easier to know what are the irreducible polynomials. Okay. Now 8, not 8, it will be 7, now 8. Okay. Suppose if belongs to R is a non-constant polynomial with f0. Since we are interested in only irreducible polynomials, we can restrict ourselves to the case that the constant is plus minus 1. And after that, because irreducibility does not change if you multiply it by a unit, I can always assume that f0 is 1, just like assuming a polynomial to be known. Then, for every polynomial g coming from R, f divides g in R if and only f divides g in C. One side is obvious. If f divides g in R, definitely it divides g in Qx. Other way, suppose f divides g in Qx. Now f has constant term 1, g is coming from R. Therefore, if g is equal to fh, the constant term of h will be just the constant term of g. Therefore, that other factor is also actually coming from R. Is that clear? Okay. What does it tell us? It has a very interesting consequence. It tells us every irreducible element of R is a prime element. So something which we always had in UFD. Now this, in spite of not being a UFD, has this very nice property that every irreducible element is a prime. Why? Because how do polynomials of R look like? They can either be constants or not constants, right? Now if it is a constant, we have already kind of agreed that only the prime numbers give me prime ideals, and prime ideals will correspond to prime elements or up to units. What about polynomials of positive degree? Suppose I have a polynomial of positive degree. Up to multiplying it by a suitable unit, I can assume its constant term is 1. Now once its constant term is 1, if it is irreducible, I think 7 tells us that it will remain irreducible in Qx. Now Qx is a PID, therefore irreducible element is prime there. Therefore, if I have an irreducible element in R whose constant term is 1, it's a prime element of Qx. Okay? Therefore, suppose some f1, f2 is divisible by f, in R. Okay. Now, if f is irreducible with constant term 1, then this f is a prime element in Qx. Therefore, f will divide either f1 or f2 in Qx. But if it divides f1 in Qx, then it divides f1 in R. Therefore, every irreducible element of R is actually a prime element. Is it clear so far? Yeah. So in fact, non-constant irreducible elements of R, of course up to units, are precisely the irreducible polynomials of Qx with constant constant are 1. Right? Because this 1 is something which you are already stressing upon. Okay, over rational numbers you can multiply it by any non-zero rational number. The property of irreducibility does not change. So upstairs you can multiply it by anything which is a rational, non-zero rational. Below, inside R, you can multiply it with either 1 or minus 1. Okay. Therefore, there is a nice one-to-one correspondence, of course, up to units. I mean, units in R means either F or minus F. Okay. So there is a one-to-one correspondence between non-constant irreducible elements of R or prime elements, because we just saw that irreducibles are same as primes. They are in one-to-one correspondence with all those irreducible polynomials of Qx which have constant term 1. So again, just making it monic. So can you tell me one irreducible polynomial in Qx which does not have constant term 1? Well, I mean up to units of course. X square plus 2. Just a moment. Which does not, well, I said up to units. So you can multiply it by half. Which will make the constant term 1. Is there any polynomial? Yeah. Up to units, can you give me an example of an irreducible polynomial in Qx whose constant term is not 1? Exactly. So that's the most natural one. X. X is the only polynomial whose constant term you can never make it 1 by multiplying it by some rational number. Whatever else irreducible polynomial I give you, you can multiply it with a non-zero rational number to make the constant term 1. So X is the only exception, and you see that X intersection R is an infinitely generated ideal. That is an exceptional case. Otherwise, whatever irreducible polynomials are there, after multiplying it by a suitable rational number, it is irreducible in R. Okay. What was this? This was 8. Okay. Hmm. Was it supposed to be 8 or 9? I suppose this was supposed to be 9, if I'm not wrong. Uh, hmm, yeah, then actually it comes 10. So every element of R, by the way, it was supposed to be 9, right? I have this is the count. Uh, See, 7 was something that it's an irreducible element of R if and only if it is irreducible in QX. So after that, 8 is supposed to be F divides G if and only if F divides G in QX. Uh, okay. Okay, then perhaps this is supposed to be 9. Yeah, I have missed the counting. Okay, sorry. Then every element of R with a non-zero constant term can be written as a finite product of prime elements. See, remember x was a problem. You cannot break it, it will continue indefinitely. However, if it has a non-zero constant term, then what you can do? First, extract the constant term, make it 1, and in other coefficients you are allowed to divide. Therefore, how does it look like after extracting the constant term? Suppose f is like this, then f will become a naught into 1 plus something, right? However, now think of it as a polynomial over q. You can get a prime decomposition. Now, to begin with, if you have taken arbitrary prime decomposition, then you have no control over the constants, but you can always make them 1 by dividing it by the constant. So therefore, always the constant will remain 1, and we just observe that they are prime elements of R. Okay? Therefore, whenever my f has a non-zero constant term, I can break it up as a finite product of prime elements. And whatever constant is coming out here, to decompose it over the ring of integers. Because every prime number is a prime element of R. So is it clear that every polynomial is a non-zero constant term? You can write it as a finite product of prime elements. So only problem is x square those polynomials. Okay. So what have we done so far? We have kind of characterized all irreducible elements of R, capital R, and we also saw that they are actually prime elements. So every irreducible element of R is a prime, and we have characterized all of them. Now finally let us look at what are the actually prime ideals of R, okay, or what is known as the spectrum of R or denoted by spec R. Okay, so let us look at what are the prime ideals. First of all, 0 is there. This being an integral domain, 0 is a prime ideal. Okay. What else is there? Principal ideals like this, where this p is a prime number. And then if such that f is irreducible in qx and f of 0, okay, and of course lastly there is an exceptional one. Do you remember what is the exceptional one? P naught, not x. It is now if you know a result known as Cohen's result, it tells us that a ring, say a commutative ring with identity. So in my world, all rings are commutative with identity. So Of course, there are some occasional intruders like rings of matrices. Okay, so yeah, so it says that if you have a commutative ring with identity, then every ideal is finitely generated if and only if all the prime ideals are finitely generated. So if you can prove that all primes are finitely generated, then all ideals are actually finitely generated. So often people what they do instead of checking whether to verify whether the ring is Noetherian, to only check it only for the prime ideals. They are finitely generated, all the ideals are finitely generated. Now look at spec R. So far we have found these four types of prime ideals. First one is of course the trivial one 0. Other two are principal ideals. Okay. However, this is the exceptional one which is not finitely generated and which is the main obstruction for R to be an Noetherian ring. Okay. Fine. And if you look at the kind of the diagram, you have maybe I should write it there. This is better. So if I draw the spectrum where ideals are becoming bigger and bigger as I go up, then what do I have? I have P naught here. Sorry. Then I have all these FIs, this kind of ideals. And finally I have all this P, the prime. Okay. So it is not a PID, of course, it is not a PID, that was obvious. But in fact, it has a chain of length 2. Okay. Not, I mean, it does not even have dimension 1, it's dimension 2. Okay. So finally, I have to show that the ideals which I have, the prime ideals which I have described so far, they are actually all the prime ideals. It does not have any other prime ideal. Every prime ideal of R looks like this. Either it is 0 or the exceptional one which we denote by P naught, which is not finitely generated, or it is coming from a prime number, or it is coming from an irreducible polynomial. Okay? Fine. So this is XR. So suppose these two are non-zero. Okay. Then what are the two possibilities? We can take the intersection of P with Z, because anyway the ring of integers is sitting inside R, right? So what are the possibilities? 0 or P, right? Now if it happens to be then it contains a prime number. And we just saw that the principal ideal generated by P is already a maximal ideal. Therefore, if this capital P intersection Z happens to be the principal ideal generated by P, it will imply that's all. But this fellow is already a maximal ideal. Therefore, this capital P will be equal to the principal ideal generated by P. So the only possibility of new prime ideals must be coming from the first one where P intersection Z equals to 0. Okay. Now, here you have two possibilities. If 0 equals to 0, okay, that's one possibility, that whatever prime or whatever member of P I choose, its constant term is 0. Okay, then because I am assuming P to be a non-zero prime ideal, it contains some non-zero polynomial. Now that non-zero polynomial is constant term 0. Therefore, I can write it as x to the power I into some g, where I is some positive integer and G has a non-zero constant term. So what am I doing? Suppose it is first coefficient is 0. I look at the first non-zero coefficient, take the x power out, then the remaining part will have a non-zero constant term. Okay. But now that G, see, R consists of those polynomials whose constant terms are coming from the ring of integers. But when I have extracted this x power out, the first coefficient here may have a rational number. So what I do? Again I clear the denominator. Because if the original polynomial is there, any integral multiple of the polynomial is again there. Therefore I can assume that the the constant coefficient of G is actually an integer. But what am I assuming? Therefore, G cannot be a member of P. So some power of x is there in P, so x is there in P. Clear? Fine. Now once x is there in P, I claim that P is equal to P naught. Why? Because pick up any Rx where R is any rational number. Okay? R square x square equals to uh, uh, x into Rx belongs to P R into R square x. Just a moment. What am I doing? Uh, I want to show that R square x square is there. Yeah, that's fine. See, only the constant term must be an integer. I don't have any restriction starting from degree 1. Therefore, I can multiply x with R square x, which becomes Rx whole square, that is there in P. And because the square is in P, Rx is there in P. Therefore, which follows, okay. But once I have gone modulo P, okay, what do I get? What is the quotient? This modulo P naught isomorphic to what? Hmm? Yeah, you will just think you are forgetting everything starting from degree 1. So what remains? The constants, which is simply z. Now, if P naught is not equal to P, then it will be something bigger. That means then it will correspond to some non-zero idea here, which will be of the form small p. But then when you contract it, you will get a polynomial whose constant term is not zero. Because there is nothing between, see, there is nothing between P naught and here properly. So if capital P happens to be containing P naught properly, then that capital P will end up being a principal ideal like this, which will say that the constant there is something its constant term is not zero, which gives us a contradiction because this is our starting assumption. Clear? Okay. Now the final piece of the puzzle, that suppose P intersection z is 0 and there is something. Okay. Observation 1. We can assume, why? Because f0 is non-zero. Again, I can extract the constant term, make the constant 1, and the remaining coefficients I can simply divide. So now because capital P intersection z is equal to 0, therefore whatever the constant term that I have extracted cannot be inside the prime ideal. Okay. Therefore f0, the other part is there. I have extracted the constant term. Therefore f0 I can assume to be equal to 1. But once I have assumed that f0 is equal to 1, I can take a prime factorization. Because in R I can do that as long as the constant term is 1, to further assume that f is irreducible. Okay, fine. But now what can happen? Either P equals to F, okay? I claim that is true. If it does not happen, then what? Then there is something G inside P such that F does not divide G. Now using a similar argument, I can assume G0 equals to 1 and G is irreducible. Because first I can take out the constant term. Because of this condition, that constant term cannot be there inside P. Therefore, the other component is there. Again, that component can be broken into irreducible parts. Now, if F does not divide G, it is not possible that it is dividing any of its factors. Okay, therefore, which implies there exists G belongs to such that G is irreducible and okay. But now we have two irreducible polynomials. They are different. So and their constant terms are 1. So they are different irreducible polynomials with constant term 1 in Qx. Therefore, they are together they are going to generate the whole ring Qx. Which implies there exists F1 G1 belongs to Qx such that if F1 plus G1 equals to 1. Now we are done because F1 and G1 they are coming from Qx, so there is no restriction on the constant term. If I want to bring them into R, I have to multiply the quantity by a suitable integer to clear the coefficient which is there in the constant term. So, but then what does it mean? If I multiply it by a suitable integer, which is the constant term, denominator of the constant term, here also denominator of the constant term, then what will happen? They will become polynomials in R. On the right hand side, you have to multiply it by something. But then there will be an integer inside capital P, which you can factorize to get the contradiction to this. Some prime number will lie inside capital P. Therefore, these are the only prime ideas of R. And I am done. Thank you for listening. Thanks. Yeah, any question? Hmm? I'm not considering it. Actually, if you know Devoto, she sent me an email with some gate question where there were some questions about this ring R, whether all irreducibles are primes, whether it's a UFD, whether it's a PID. So then I started thinking about this ring, and these are the properties which I could observe. And it is of interest because I'm lecturing on it. So that's from my perspective. And I mean, this is a general construction. I mean, if you want to know, I mean, not particularly taking integers or rational numbers, but if one asks you to give some example of non-Noetherian rings, so this is a standard procedure in by which you can construct non-Noetherian rings. You start with any integral domain which is not a field. Okay, then you take the polynomial, I mean, set of all polynomials from QAX where the constant term is coming from A. Then it always happens that it's a non-Noetherian. So in that setup, I was aware of this kind of examples. But I never thought it putting A particularly to be the ring of integers and then taking its field of actions. But in general, this is the standard technique to construct non-Noetherian rings. Okay. Anything else? Okay. Hmm. Yes. Yes. How? Because you know the correspondence between prime ideas of the quotient and ordinal ring. So look at the quotient. There is nothing between 0 and P. That's the idea. Here 0 corresponds to P naught and small p we are denoting it by again ideal generator form. That's all. Okay. Nothing else? Thank you. Okay. Yeah, you're welcome. Tell. I'll have to see at night what happens. I mean, it was slightly troublesome. Now it is not still not okay. So let's hope it will get better.